Hey everybody, welcome to Chapter 3. I'm going to give you a little bit of a warning up front. This is like a super long lecture. I mean, not super long, but it's long. There's a ton of slides that the manufacturer put out, but I think they're valuable, so I'm going to go through them with you. If you need to, you can always, the beauty of doing this recorded is you can always skip forward or skip back as you need to. So Chapter 3 is what we call descriptive statistics, or statistics that tell us about something. There's the map. You can see there's a ton of stuff to cover. And I'll just get to it. So the first thing we're going to talk about are what's called measures of central tendency. Or in other words, the different ways we can sort of describe the center point of a data set. We'll start with the mean, the median, and the mode. You've probably heard of all these and learned about them in school. So I'll go through it fairly quickly. And of course, you can always slow it down or roll back as you need to. So the mean is what we often call the average, right? And all we do is really add everything up and then divide by the number of observations. So this is the formula. And the reason I like to show you the formula is because it looks really intimidating. It looks like some kind of crazy math. Even though most of us know how to find the mean or the average of something. Mean is always denoted by x with a little line over the top that we call x bar. Which is the mean. So again, you see that formula. All that means is the sum of each of the values of x divided by n, which is the number of data values in the set. That's it. You can see the formula for the population mean is the same. It's denoted by the Greek letter mu, and that would be just the sum of all the values in the population divided by the number of data values in the population. So really the same formula whether we're looking at a sample of a population or of the whole population. There's a sample of how you calculate it. I won't explain it to you. You're smart. You add them up. You divide by the number there are there, and it gives you a 6.08. Sometimes we want what's called a weighted mean. That allows us to assign more value to certain values and less to others. We do this a lot like in our grade books, right, where we say exams are worth 35% and homework's worth 25%, etc. And so we weight the average based on wanting certain parts of the average to be worth more of the total. So now it's the sum of W times X, where W is the weight of each data value. And X is each data value. Again, these formulas make it look scary, but as you work them out, you'll realize it's not that hard. Anyway, you take the sum of the W times the X and then divide it by the sum of W. That's all. So here's an example. If you already summarized the number of days you worked each week for a sample size of n equals 20 weeks into this table. So on some days, some weeks we worked 3 days, some 4, some 5, some 6. And then there's the frequency, how often that occurred. So if we want to find the average number of days worked per week, we need to give more weight to the 4 days because there were more times when we worked 4 days and less to 6 days because there were less times. So the way we do that is we take our W times our X. Actually, so it's a little confusing the way they did this. So the red, the frequency, represents the W, how often we observed it, and the blue, number of days worked, represents the X, or the data point of interest. So we multiply those, 4 times 3, 7 times 4, 6 times 5, 3 times 6. And then in the denominator, we just take the sum of all the W's, 4, 7, 6, and 3. And that gives us a weighted mean. Piece of cake. The reason we like to use the mean is it's super simple. We know how to calculate the average, and Excel will do it super quick. And I'll show you how to do all these things in Excel when we do the guided problems. The disadvantage is sometimes it throws things off. If we have extreme outliers, like in these two samples, it can look like in sample 1, the data is very close to each other. In sample 2, we have a really high number, a really low number, and one in the middle. And it looks like it's the same data set when you just look at the X bar or the mean. So the median is the value in the data set that's right in the middle, where half the observations are higher and half the observations are lower. So all we really do to figure out the median is arrange the data in ascending order, in other words, from lowest to highest. We use an index point, and we calculate that index point by doing 0.5 times n, where n is the number of observations in the data set, and that tells us the index point, not the number, but the order of the number. So here's the n of 7. They're arranged in order from lowest to highest. The index number is found by taking 0.5 times n, so 0.5 times 7 is 3.5. And then the index number, if it's not a whole number, we just round up to the next value of I. So in this case, we'll find our median is at the 4th point in the data set, which is the number 28. What's cool about median is it doesn't care that much if we have huge outliers, like a giant number at the top. That's easy. When there's an odd number of data, or of items in the data set, the median is always the middle value of the data set. When there's an even number, we're going to have a decimal like we did on this one, 3.5, so we round up to the next higher index point. Here's a couple rules. I won't read it to you. You can read it. The mode. The mode is the value that appears most in the data set. So it's the most often, the one that's most often. And it has nothing to do with, adding up, dividing. It's just which one's there the most. So if we look at this data set that has 0, 1, 2, 3, 4, and 5, if we do a frequency distribution, it's easy to see that the number 2 occurs the most often, and therefore that is the mode. That's all. Same thing here. There's more Toyotas than others, so Toyota is the mode. It's the one that occurs the most. So here's an example. 5 homes. To find the mean, we add all of them up. We divide by 5. That gives us a mean price, $600,000. To find the median, we find the middle value of the ranked data. So you can see they're in order. If there's 5 of them, we divide that, or we multiply that by 0.5, and we get data point or index point 2.5. We round that to the next whole number, so that's 3. So we just start from the lowest and move up to the highest, 3 index points. 100,000 is the first one, 100,000 is the second one, 300,000 is the third index point, so that becomes our median. And the mode is the one that appears the most often. And we see that 100,000 appears more often than the others, so that becomes our mode. All right, so when we do a frequency distribution, which we learned about in Chapter 2, and we plot it out, remember this just shows the number of times that each data point occurs. It's usually shaped one of 3 ways. There can be a 4th way where it has kind of no particular shape. But usually it's either symmetrical or it's skewed. And you'll notice that the mean and the median on a symmetrical frequency distribution are both right in the middle. Whereas when you have a left skewed distribution, the mean is to the left of the median. And when you have a right skewed, the mean is to the right of the median. That's all. Piece of cake. You're like, it sounds like a piece of cake. All right. The cool thing is you don't have to do all this by hand. Excel has functions to do this. The mean, you use the function equals average, and then you highlight the data set and it'll calculate it for you. The median is equals median, and mode is equals mode.sngl. The problem with using Excel for mode is if there's more than one mode, Excel will incorrectly display only one of them. So you have to kind of keep an eye on it. It doesn't work well for that. You can also use the data analysis tool that we talked about in Chapter 2. And it will give you a whole bunch of summary statistics, including the mean, median, and mode, and a few others. So the question is, which one should I use? Is mean, median, or mode better? I'll say in real life, sometimes you use different ones depending on your needs. Mean is kind of the most common. We know what the average is, and we use that the most. If there's giant, huge outliers where like certain data points that fall way outside of the rest of the data, then the median is often a better measure of central tendency. And when we have categories or categorical data, then the mode is the best choice. There's a summary of advantages and disadvantages. Again, I won't bore you by reading it to you. If you need more time, you can pause it and read that. All right. Excuse me. So next we have measures of variability. In other words, how spread out is the data set I'm looking at? Measures of variability are broken into range, variance, and standard deviation. And then you'll notice that variance and standard deviation, it says that we do it a little differently for a sample and for a population. And that'll become more important as we move through the course. So to find the range of a data set, all you do is you take the highest value in the data set minus the lowest value in the data set. That's the range. That's it. Of course, the advantage is that it's easy to deal with. The disadvantage is that you're trying to summarize a whole data set based on only two numbers that are in the data set, and outliers can really throw it off. All right, so variance and standard deviation. Sample variance is always denoted by S squared. And you see this formula, again, it looks a little scary, but it's not. And once you get into the example problems, you'll see it's not too bad. But it's the sum of each value of x minus x bar, or minus the mean of x. And you square that, and then you divide it by n, which is the sample size, minus 1. So here they give us a sample set. We find the mean, which is 10 in this case. And then to find the variance, we just take each data point, so 4 minus 10 squared plus 6 minus 10 squared plus 8 minus 10 squared, etc. Do each one, and then divide it by n, which is 8 minus 1. And our variance is 18.571. This is a measure of how spread out the data is. The standard deviation is just the square root of the variance. So standard deviation is denotated by just an s. Remember that variance was s squared, so the square root of that is s. So same thing, we just take the square root, and that's our standard deviation. We'll learn a lot more. Standard deviation will become important throughout the whole course, but I know it's probably a new concept to most of you right now. Here they call them equivalent but easier for hand calculations. I think it looks more confusing. Nonetheless, there is the information. I'll also show you how to do it in a table in Excel, and then how to use a function in Excel to calculate variance and standard deviation. When the data set represents an entire population, then we have a formula which is exactly the same, even though it looks different, and I'll tell you what I mean by that. So the variance is now just the sum of each value of x minus the population standard deviation divided by the big N, which is the population size. So it's exactly the same as we do in a sample, except we're dealing with the total population now. And then the square root of it is the population standard deviation. So they're going to give us an example. I'll let you look at that if you want to, or you can pause it if you want to. But we can use these Excel formulas, which will make your life happier. I'm going to teach you another way to do it, which will help you understand what it is better, but it won't be easier than using these Excel formulas. If we're dealing with a sample, it's var.s, and then the data values. And if we're dealing with a population, it's var.p. Also, our Excel's descriptive statistic tool, the one we just talked about a minute ago, can be used. It returns standard deviation and variance and range. All right, so this is where we start to get into concepts that are going to stick with us for the rest of the course. The first is that standard deviation is a common measure that we use all the time in business. The reason is because it's standard, and that makes it really easy for us to measure things using it. So one of the things we have to use is something called the coefficient of variation. This will measure our standard deviation as a percentage of the total mean. I realize I just read that to you, but that's what it does. That means a smaller coefficient of variation means our data set is more consistent, less spread out from the mean. So there's the formula for the coefficient of variation. It's just the sample standard deviation divided by x bar, the sample mean, and then multiplied by 100. Population's the exact same thing except using the population numbers. So, for example, if we wanted to figure out how much variation there is in a certain stock, we could calculate the coefficient of variation for it. The standard deviation, $4 divided by the average price times 100. For stock A, that makes it 8%, and for stock B, it's 5%. That means that stock B is actually more consistent and has less deviation around the mean of its price. And this leads us to a discussion of z-scores. A z-score is a measurement of different data values, but instead of using an arbitrary label, like we could be measuring minutes or hours, I guess those aren't arbitrary, but those are descriptive, we're going to take everything to a standardized units. And the units for z-score, this says a z-score has no units. I disagree with that. A z-score, its units are standard deviations. If we say we have a z-score of 1, that means we are 1 standard deviation above the mean, or higher than the mean. If we had a z-score of -1, it would mean that we are 1 standard deviation below the mean, or lower than the mean. So even though it says it has no units, I disagree. Z-score units are standard deviations. It doesn't have units in the sense that it's measured in pounds or dollars or whatever we're using to measure the data. This measures how how far away from the mean a given data point falls. It's a big thing on the bottom there. If it falls above 3 or below -3, then it's so far away from the mean that we would consider that to be an outlier. So to find the z-score of a population, of a given data point in a population, all you do is take x minus the population mean divided by the standard deviation. And for a sample, it's x minus the sample mean divided by the standard deviation. So here's an example. If we want to figure out, in this case, it looks like we're going to figure out where a Burger King Whopper sits as far as is it way more or way less than others. We could ask ourselves, how far is 670 calories, number of calories in a Whopper, away from the sample mean? So we could calculate the sample mean pretty easily, right, just by adding those all up, dividing by the number of items there. And the sample mean is 776.3. And then if we know that, we can also calculate the sample standard deviation, and they already did that for us, 385.1. So then if we want to choose a particular value of x, in this case, they're choosing the Whopper, so 670 calories minus the mean of 776.3 divided by the standard deviation. This is going to give us a z-score of negative 0.276, meaning that the Whopper's caloric count is 0.276 standard deviations lower than the mean. That means the Whopper is a little bit healthier than the average fast food hamburger. Okay, so the value of these z-scores is now it kind of takes all of the units out of consideration and just allows us to compare things on a standardized scale of standard deviations away from the mean. And this leads us to something called the empirical rule. An empirical rule tells us, the empirical rule tells us that if a distribution follows a bell-shaped curve, like the ones you see here, then 60, and that's also called a normal curve, okay? That 68% of the values will fall within plus or minus 1 standard deviation, 95% will fall within plus or minus 2, and 99.7% of all the values will fall within plus or minus 3 standard deviations from the mean. This is valuable to us as we're trying to understand if we should include certain values or if we should reject certain values. I said earlier that if it falls outside of plus or minus 3 standard deviations, we would consider that an outlier, right? Because the area outside of plus or minus 3 standard deviations represents 0.3% of the entire data set, because 99.7% of the data set is included in that whole range from -3 standard deviations to +3. So sometimes we would want to express the z-score in terms of x, and then all we would do is follow these formulas. Not too bad. So where we take the mean plus the z-score times the standard deviation. So here's our question: for symmetrical bell-shaped population with a mean of 20 and a standard deviation of 3, what interval will contain about 95% of the values? Remember that we say plus or minus 3 standard deviations will contain 99.7, but we have to find 95%. And that's contained within plus or minus 2 standard deviations. So if we take 20, that's our mean, and then we add 2, that is our z-score, times 3, the standard deviation of the sample. I'm sorry, this is a population. That gives us 26. And then if we take the mean minus that gives us 14. So what that tells us is that 95% of all the values will fall between -2 standard deviations, which is 14, and +2, which is 26. All right. We can also look at Chebyshev's theorem, and this is a theorem that we use if we don't know whether or not we have a normal bell-shaped curve like we use for the empirical rule. In this theorem, we realize that regardless of the shape of the distribution, even if it's not bell-shaped, even if it's much different, that still 75% of all the data values fall within plus or minus 2 standard deviations, 89% within plus or minus 3, and 94% within plus or minus 4. So even if we don't know the shape of our distribution, which often happens in real life, we can still use Chebyshev's theorem to get a good idea of where a data value, a given data point, will fall in the whole range of data points. All right. So sometimes, though, it's not so simple as just working with each data point. Oftentimes in real life, we're dealing with information that is grouped, meaning we don't have an exact number for each value we want to measure. Instead, we might have a range of values. So to estimate the average for a frequency distribution, remember we talked about the size of the number of classes that we would divide something into, and then the range each of those classes would cover. So if we want to estimate the frequency, the average, what we have to do is find the midpoint of each group and use the midpoint as a representative value for the whole group. And then we could get an approximate mean. That's x bar. You see that there? That's the mean. And that will equal the frequency, or the number of times that class is represented, times the midpoint of the class divided by n, or the number of total observations. There's the formulation, or the formula. So let's look at an example. An online merchant has collected the following group data for a number of web pages viewed by a sample of its customers. So now you can see what I mean by there's a range, 1 to 5, 5 to 9, 9 to 13, and 13 to 7. And then a frequency, the number of times each of those ranges occurred. We need to calculate the average number of viewed pages. Well, that's hard to do. So all we can do is really estimate it. So we'll find the midpoint between 1 and 5. 1 and under 5, we're going to call the midpoint 3. 5 to under 9, the midpoint is 7. 9 to 13, 11. 13 to 17, 5. And then we multiply that by the frequency of each. Looks a lot like a weighted average mean, doesn't it? And that gives us the numerator, and then the bottom we just do by the total frequency. So 6 plus 12 plus 10 plus 4. And that'll give us an approximate average of 8.5 pages viewed. To find the variance and standard deviation of group data, it seems a little complicated if you look at the formula here, but it's not crazy. Again, it's just the midpoint minus so the midpoint of each group minus the mean, the x bar squared, times the frequency divided by n minus 1. You'll notice when we do the population, we don't do the minus 1. It's just divided by the big N, or the total number of points in the population. So there's a little difference between those two formulas, whether we're dealing with a sample or a population. So again, here's our data. So we just take each midpoint, subtract the average, which we found just a minute ago, and then multiply it by the frequency. And then we divide that by n minus 1, and that will give us a variance of 1.419, and then we just take the square root of the variance to find the standard deviation. That's it. All right. Now we'll consider measures of relative position. I told you there was a lot of stuff in this chapter. I warned you, but you still had to watch it. I know. I'm sorry. The two different measures of relative position we're going to deal with are percentiles and quartiles. Percentiles tell us the approximate percentage of values in the data set that are below the value of interest. If you think about some of the standardized tests you had to take, like ASVABs, they would always return a percentile score. So if it said you got in the 80th percentile, that means you scored as well as or better than 80% of the people that took the test. That's all a percentile means. So this is a little confusing when it says the pth percentile of a data set is the value that at least p% of the observations will fall below that. So there's the kind of examples where they try to explain it. To find a percentile manually, all we do is we find an index point where the index point is equal to p, the percentile of interest, the number we're looking for, divided by 100 times n, which is the number of data values. There's a few rules here. I'll let you read those, and they're in your book too, so you'll have to apply them when you do the homework. So here's an example of percentiles. They recorded MPG miles per gallon for 12 cars. They ranked them in order. And then the question is, which value is the 60th percentile? So if I take P and make that 60, that's my percentile of interest, divided by 100, multiply it by 12, I get 7.2. Then it tells us I round up to get the next index point. So the 8th position, the data point in 8th order, becomes my 60th percentile, 31.1 miles per gallon. You can also use Excel to calculate percentiles using the function percentile.exe. The downside is that Excel rounds a little bit differently, and so it's off by a little bit from what you would do if you calculated it manually. It's actually, the Excel version is actually more accurate. Percentile rank identifies the percentile of a particular value within a set of data. So in order to do that, we take the number of values below x plus 0.5 divided by the total number of values times 100. That'll give us percentile rank. So what's the percentile rank of the car with 35.8 miles per gallon? We see it's in the 10th position. So we take the number of values below it, which is 9, plus 0.5, divide that by 12, multiply by 100, and we find that that is in the 79th percentile, meaning 79% of data points are equal to it or below it. Quartiles are just splitting it into 4 equal groups, okay, splitting ranked data into 4 equal groups. I'll let you read that. So if we have a data set, we want to split it into 4 equal groups. We find the index point where n equals 11 and p equals 25, and that tells us 2.75. So the third item, which is 13, becomes our first quartile. That means 25% of the data are at 13 or below. We repeat the process with 50 to get the second quartile, 75 to get the third quartile. We can also use quartile.exe in Excel. The interquartile range describes the middle 50% of the range, or in other words, quartile 3 minus quartile 1. Sometimes they use something called a Box-and-Whiskers plot. I don't know if you guys can tell, I'm starting to run out of steam. This is a lot of information, so I'm going to stand up so I have a little more energy. A Box-and-Whisker plot is a graphical display showing the 3 quartiles. And all you do is you show the outliers way out on the ends. And then the whiskers, they stick out to where there's the lowest value that is not an outlier on each side. And then the box shows the first quartile, the median, which is the second quartile, and the third quartile. The formula for the upper and lower limits of outliers is the Q3 plus 1.5, so the third quartile number plus 1.5, and the lower minus 1.5. Anything beyond that we consider an outlier. So there's some instructions on how to draw it. Again, I won't read it to you because you're smart. So here's an example of constructing one. First, they calculate the index points and figure out that the first quartile is at 1.39, the second at 2.71, the third at 3.45. We determine the upper and lower limits for outliers by taking the third quartile plus 1.5 and the first quartile minus 1.5. We see that Great Smoky Mountain is above and is an outlier. Now we can see there's our minimum, 0.39. That's the lowest data set or data point in the set. First quartile at 1.39. There's the box. Second at 2.71. Third at 3.45. Fourth at 4.42. That's the highest that is not an outlier. And then we mark the outlier out there with an asterisk. That's a Box-and-Whisker plot. Something similar is called a 5-number summary. I actually prefer this if someone needs to report this data to me, because instead of all the confusing visualness of the Box-and-Whisker plot, this just shows me the minimum, the maximum, and the 3 quartiles. The only downside is outliers aren't included in a 3-number or a 5-number summary. All right, last 2 things. Measures of association between 2 variables. In other words, before we were looking at like a single data set with one variable. We would pick one value of x out of the whole data set. Now we're trying to see if we have 2, an x and a y, how closely are they related or associated with one another. And so we'll look at covariance and correlation coefficient. So to calculate covariance, again, there's this scary looking math formula, and you'll see it's notated by S sub xy, okay? All we do really is we take the sum for each value of x minus the mean of x times this, so we take, and then the sum of each value of y, or I'm sorry, times the sum of each, not sum, I take this back. So it's each value of x minus the mean of x times each value of y minus the mean of y, and then the sum of all of those, okay? And divide that by n minus 1. That's the covariance. Then we have the correlation coefficient, where we have the covariance divided by the standard deviation of x times the standard deviation of y. So here's an example. We have a car dealer wants to examine the relationship between the number of sales representatives and the number of cars sold. So each week they record how many sales representatives they had and how many cars they sold. And there's the data set. You can plot that on a little scatter graph and see that there looks like a pretty good relationship, right? When there's more sales reps, they sell more cars. So if we want to calculate the covariance, we can figure that out, right? Number of sales reps, and then the x bar, the mean of all of the number of sales reps. Then we do x, each point of x minus y, minus x bar. Then we do the same thing for all the y values. And then we sum them up, and we come up with 10. N minus 1, so n was 6 minus 1. We come up with a covariance of 2. Here's what it means. A positive value implies a positive relationship. It's linear. A negative covariance indicates a negative linear relationship, and a covariance close to 0 indicates that there's no relationship between these two. So here we can see with a 2.0 that that is a pretty good relationship. The more people we have working, selling cars, the more cars we sell. Correlation coefficient, again, we find x bar, y bar, that's just the mean. And then we take, we have to find the standard deviation of x and the standard deviation of y, and then we can calculate it. So we know the correlation, or the covariance was 2.0 divided by the standard deviation of x times the standard deviation of y, and that comes out to a correlation coefficient of 0.952. What's cool about correlation coefficient is it's always a number between -1 and +1. And so the closer it is to +1, it's a strong positive relationship. The closer it is to -1, it's a strong negative relationship. And what a positive relationship means is that each time x goes up, y goes up. So if you had a correlation coefficient of 1, it would mean that x goes up by the same amount as y each time, or by the same amount. Each increase to x produces the same increase to y each time. If we have a negative, it goes the opposite way. So an increase to x creates a decrease to y. So this tells us not only the direction, but also the strength. The closer it is to 1, the better the relationship. In this case, we had a 0.95. So I think that proves that we need to have more salesmen if we want to sell more cars. There's some examples. You can see what a 1 looks like and a -1. 0.6, -0.4, and then a 0 where there's no real relationship between x and y. And that is the end of Chapter 3. Like I said, I know it's a ton of information. You can run through this more if you need to. You can pause it at points. I rushed it, which means I went through it really fast, assuming that that would give you the ability to kind of slow it down where you need to. Have a great week, and good luck with Chapter 3.